Have you ever wondered why, if the Earth is spinning on its axis and rotating around the Sun, we do not sense this motion? Have you ever seen on TV and wondered why, when the person pulls the tablecloth from under the plates and dishes, the dishes do not move? Or how about, have you ever seen a demonstration where someone lays down a bed of nails and a cylinder brick is smashed on their chest with a sledgehammer and yet nothing happens to them? Well, the answer to all of these are coming up in this lesson, where we will be learning about Newton's first law. Now, our first question of why we not sense the Earth's movements were also questions that troubled Galileo as he was using telescopes to prove Copernicus's heliocentric model. But what he came up earlier in his career is he realized something called inertia. And inertia kind of helps explain this as well. So Galileo realized that objects liked to resist acceleration. So basically, inertia is the resistance of acceleration, and inertia depends upon mass. The more massive you are, the more easier it is for you to resist motion. Now that brings us to one of our other questions here. When we look at the bed of nails trick, where a person lies down on a bed of nails, like here, and then another person has a sledgehammer and there's a cylinder block across the person lying on the bed of nails, and he hits it hard with the sledgehammer, and yet the person remains unharmed. Why does this happen? Well, remember, Galileo came up with this idea of inertia. So that big, heavy cylinder block does not want to move. So when he hits it, the cylinder block absorbs all of the force of the sledgehammer, and the person does not have the nails sticking through him. There's a second physics thing happening here. When the person lays down on the nails, there's hundreds or thousands of nails, so his weight is divided evenly amongst the nails. If there's only like 10, 20 nails, then that'd be like a medieval torture device where the nails would pierce through them and their weight is not evenly distributed. But anyway, the force of the hammer is absorbed through the cylinder block as the cylinder block normally collapses, because the cylinder block has inertia. It is going to resist movement. Now the same idea here is when we look at the tablecloth experiment. So when we pull the tablecloth with all these dishes on top, the mass of these dishes does not want to move. There's inertia. They're going to resist the movement. So then they are barely going to move, and the tablecloth, if you pull it fast enough, is going to move only. And once again, that's inertia. So this idea of inertia was later then expanded by Newton. Newton modified and extended Galileo's idea about inertia to come up with the first law of motion, of his three laws that is, and that is an object will continue to be at rest or moving at a constant velocity unless acted upon by an external force. So let's take a look at my two examples here. Let's look at my first example. We have a man just standing there. We know the net force is zero. He has two forces acting upon him. He has the force of gravity, and he has a normal force. And these balance out to be zero. So he does not move. Now let's look at my second one here. This is a little bit more trickier. We have a constant velocity, but that means my net force is zero in this case. So in this case, if we draw a free body diagram, we know my Fn, my normal force, is going to be equal to my force of gravity. We also know in this case, my applied force is equal to my force of friction. So they feel no force. So this means if you want to change the motion of an object, you will need a non-zero net force to be applied to the object. So I have a little concept check for you here. The Voyager 1 and 2 space probes move in space at 70 kilometers per second. There is no external force that exists on the probe. I want you to describe the motion of the probe. Pause the video, think of a couple of seconds, see if you could describe the motion of the probe. Welcome back. If you said that the motion of the probe is uniform motion, you are correct. So now let's apply Newton's first law of inertia to our driving in vehicles. Many of you have started driving and you might have taken a corner a little bit too fast. Or when you're on a snowmobile or a Sea-Doo or even a side-by-side and you take a corner too fast, something happens. You feel the inertia. Your body wants to go one way while your vehicle goes the other way. Let's see why that happens. If we are taking a corner, so let's say this is my road here, and I am driving in this direction. Right now, all of my velocity is Vy. Then all of a sudden, I turn to go into this direction. In order to turn, my Vy is actually getting smaller. And in this case, my Vx is going to be getting bigger. So what that means is that I now have a negative acceleration in my Vy and a positive acceleration in Vx, which is a force being applied to us. This whole idea of inertia is what makes roller coasters so much fun. We are changing directions. We're accelerating from one way to the other, and our inertia is what takes us and moves our body in the ride, or when we're having fun on a snowmobile or Sea-Doo or something like that. Because our bodies want to keep doing what they are doing. That's the whole idea of Newton's first law. If our body's in motion, it wants to stay in motion until a force is acted upon us. So in a snowmobile, we have to either lean into the turn or hold on super tight, otherwise we fall off. So now let's consider a car hitting a brick wall and there's no airbag and you also forgot to wear your seatbelt. Let's see what happens. So basically what happens here is your body wants to keep on moving. There's nothing holding your body back because an option that is in motion will want to stay in motion unless an external force is applied to it. There is no external force here, such as a seatbelt or an airbag, to prevent you from flying out and getting hurt. So here's something I want you to think about. I want you to use Newton's first law of inertia to explain why steel barriers are used to separate the cab of big semi-trucks from the load. Or trucks carrying tall loads navigate corners very slowly. Another thing I want you to think about is why when you go to Tim Hortons or McDonald's and you order a coffee or any drink, they are putting lids on them. So be ready to answer these questions using Newton's first law in class. If you're confused on some of these questions, let's look at this truck here. In this truck, in this section here, we have a steel barrier that is used to separate the cab from the load. So there's this huge steel barrier here. Use Newton's laws to explain why that barrier is there. If we look at this is a huge load, lots of mass. Why do these trucks need to take corners even slower than regular vehicles? And then the last one is, once again, why do we need lids on our drinks? So that's it for today's class. See you in class.